In this video, we are going to calculate the Laplace transform of right-sided and left-sided sinusoidal signals. So let us start with the exponential, complex exponential signals. So let x1 of t be e to j omega 0 t u of t. Okay, again, let us carry out the calculations simultaneously for the right-sided and left-sided signals. So x1 of t is a right-sided signal, and it's exponential, complex exponential signal with real part equal to cosine omega 0 t and imaginary part sine omega 0 t. Okay, x1 of t is right-sided signal. It is 0 for negative values of t, in other words. And let x2 of t be equal to minus e to j omega 0 t u of minus t. Now here I put this minus sign just for the following reason. We are going to obtain the same expression for the Laplace transforms of x1 of t and x2 of t, but their convergence regions will be different. So just to obtain the same expression, I put a minus sign over there in x2 of t. So x2 of t is left-sided. Okay. Now, what is the Laplace transform of x1 of t? x1 of s is equal to, okay, let us write it directly. It will be the integral from minus infinity to plus infinity, but since we have u of t, the integral will start from 0 and the upper limit will be infinity. E to j omega 0 t e to minus st integrated with respect to t. Similarly, x2 of s will be from minus infinity to 0. Now we have u of minus t. Therefore, for positive values of t, we will have 0 minus e to j omega 0 t e to minus st integrated with respect to t. Okay, now remember, here s is our complex variable, sigma plus j omega. Okay, and in the integrations, the imaginary exponents will have no role on convergence of the integral because they are just sinusoidal functions. So only the exponential terms with real exponents will have a role in convergence of the integrals. So x1 of s exists if real part of s is sigma is positive, because we will have a decaying exponential over the interval from 0 to infinity, which will be integrable, of course, or absolutely integrable. The remaining terms will have magnitude equal to 1 because they are complex exponentials. And similarly, x2 of s exists if real part of s is negative. Because when the real part of s is negative, again we will have a decaying exponential as in the interval from minus infinity to 0. When t tends to minus infinity, we have a decay behavior, and therefore, again, the integral will converge. And x1 of s will be, therefore, 1 over j omega 0 minus s e to j omega 0 t e to minus st evaluated at 0 and infinity, the integration limits. When t tends to infinity, we know that real part of s is positive, therefore this will decay to the exponential, real exponential with the real exponent will decay, and therefore the result of this integral is 1 over s minus j omega 0. Similarly, now x2 of s will be equal to with a minus sign, minus 1 over, again, j omega 0 minus s e to j omega 0 t e to minus st evaluated at the integration limits. Now st tends to, this will be minus infinity. As t tends to minus infinity, again, we have exponential decay because we have chosen real part of s to satisfy this inequality, real part of s less than 0. So x2 of s will be equal to, again, 1 over s minus j omega 0. So x1 of s is 1 over s minus j omega 0, and region of convergence for x1 of s is all those s such that real part of s is, okay, let me write it here. Region of convergence is all those s such that real part of s, or sigma, greater than 0. So on the s-plane, the region of convergence will be this half plane, sigma greater than 0. And similarly, x2 of s is 1 over s minus j omega 0, the same expression. However, the region of convergence is all those s such that real part of s is negative. In other words, if we plot the s-plane, the region of convergence will be the half plane, sigma less than 0. Okay, so for the complex exponential signals, we have this result. Now, we can use this result, or the Fourier transforms of x1 of t and x2 of t, to calculate, for example, the Laplace transform of cosine omega 0 t, u of t, or minus cosine omega 0 t u of minus t. Okay, they are going to have the same Laplace transform expression again, but their convergence regions will be different, of course. Now let us look at that problem. Now again, let us consider right-sided and left-sided sinusoidal signals. So let y1 of t be equal to sine omega 0 t u of t. Okay. So y1 of t is right-sided. Okay, again, let us perform the calculations simultaneously. And let y2 of t be minus sine omega 0 t u of minus t. Okay, minus sine omega 0 t multiplied by the signal u of minus t. So y2 of t is left-sided. Okay. Now we can, of course, do the following. We can write down the function sine omega 0 t u of t in the Laplace transform integral and evaluate the integral by using integration by parts. Similarly, for y2 of t, we can do the same thing. But we are not going to use that approach. Instead, we are going to express y1 of t and y2 of t in terms of complex exponential signals and evaluate the Laplace transform by using the Laplace transforms of those complex exponential signals. So y1 of t can be written as 1 over 2j e to j omega 0 t minus e to minus j omega 0 t u of t. Similarly, y2 of t is, now we have a minus sign, minus 1 over 2j e to j omega 0 t minus e to minus j omega 0 t u of minus t. Now we remember the following. We remember the Laplace transform of e to j omega 0 t u of t, or minus e to j omega 0 t u of minus t. Okay, so we have e to j omega 0 t. This has the Laplace transform 1 over s minus j omega 0 with the convergence region. Okay, let me write it over there. The convergence region here for this case is all those s such that real part of s is positive. And here we know that minus e to j omega 0 t, of course we have u of t, I have forgotten to write that down, e to j omega 0 t u of t has this Laplace transform, and minus e to j omega 0 t u of minus t has the Laplace transform 1 over s minus j omega 0 again with the corresponding convergence region, all those S such that real part of S is negative. Okay? So, now, in fact, we have not yet studied the linearity of the Laplace transform. The Laplace transform is an integral. We have the Laplace integral, and therefore it's a linear operator. Therefore, we will be able to calculate the Laplace transforms of the two individual complex exponential signals and add the result to obtain the Laplace transform. So y1 of s can be directly written as 1 over 2j 1 over s minus j omega 0 minus. Now, although we have not calculated the Laplace transform of e to minus j omega 0 t u of t, the only difference here is that omega 0 is replaced by minus omega 0. So, this will be equal to minus 1 over s plus j omega 0. Okay. Similarly, y2 of s will be 1 over 2j. Okay, we will have exactly the same expression because we know that the Laplace transforms of e to j omega 0 t u of t, the right-sided complex exponential signal, and the left-sided complex exponential signal given by minus e to j omega 0 t u of minus t are exactly the same expressions. So we have 1 over s minus j omega 0 minus 1 over s plus j omega 0. So if we just try to obtain a simplification, we have in the numerator we have s plus j omega 0 minus s minus j omega 0 divided by the product is simply s squared plus omega 0 squared, and therefore the s terms will cancel out. We have j omega 0 plus j omega 0, so we have 2j omega 0. So we have omega 0 divided by s squared plus omega 0 squared as the expression for y1 of s. Now, since y2 of s is exactly the same result, we have omega 0 divided by s squared plus omega 0 squared. So again, these two signals, one of them is right-sided, the other is left-sided. They have the same Laplace transform expression. However, their convergence regions are different. So the convergence region for y1 is all those s such that real part of s is positive. And the region of convergence for y2 is all those s such that real part of s is negative. Okay? So we have we have just calculated the Laplace transforms of the right-sided signal sine omega 0 t u of t and the left-sided signal minus sine omega 0 t u of minus t. Now that minus sign is just for the sake of obtaining the same expression for the Laplace transform in both cases. However, the convergence regions are completely different, and in fact the intersection of the convergence regions is empty, and therefore if we add y1 of t and y2 of t, we are going to obtain sine omega 0 t, but its Laplace transform does not exist. So, as a final remark, y1 of t plus y2 of t is simply sine omega 0 t y1 of t minus y2 of t, because we want to obtain sine omega 0 t. So sine omega 0 t u of t, sine omega 0 u of minus t. When we add them up, or in this case, of course, subtract y2 of t from y1 of t, we obtain sine omega 0 t, but Laplace transform of sine omega 0 t does not exist. Why? Because ROC1 intersection ROC2 is the empty set. Okay. The reason that the Laplace transform of sine omega 0 t does not exist is that we are not able to obtain the Laplace transform of the sum of these two signals, because each signal has the Laplace transform of each signal is defined on a different part of the S-plane, the region of convergence, and these convergence regions do not overlap. They have an empty intersection, and as a result, the Laplace transform of sine omega 0 t does not exist. Okay, we can carry out the similar calculations for cosine omega 0 t u of t and minus cosine omega 0 t u of minus t. So, well, that will be exactly the same approach, but let us just write down the results for the sake of completeness. Let us do this next. Okay, now let z1 of t be cosine omega 0 t u of t, and again we are going to calculate the right-sided and left-sided cases simultaneously. Let z2 of t be minus cosine omega 0 t u of minus t. So z1 of z1 of t is of course expressed in terms of a superposition of the complex exponential signals. So we have 1 over 2 e to j omega 0 t plus e to minus j omega 0 t u of t. And similarly, z2 of t here will be minus 1/2 e to j omega 0 t plus e to minus j omega 0 t u of minus t. Okay, we can write down the result immediately because we remember the Laplace transform of the complex exponential signal. So this is equal to z1 of s is equal to 1 over 2 1 over s minus j omega 0 plus 1 over s plus j omega 0. And z2 of s will exactly be the same expression, 1 over 2 1 over s minus j omega 0 plus 1 over s plus j omega 0. And the region of convergence here will be all those s such that real part of s is positive. And here the region of convergence is all those s such that real part of s is negative. Okay, very similar to what we have done for the previous cases. Okay, z1 of s can be simplified as follows. We have 1 over 2 s plus j omega 0 minus s minus j omega 0, sorry, plus s minus, okay, s plus j omega 0 plus s minus j omega 0 divided by s square plus omega 0 square. So here the imaginary terms will cancel out. J omega 0 and minus j omega 0 will cancel out. And we have 2s divided by 2. So we have z1 of s is s divided by s square plus omega 0 square. Okay. And z2 of s is similarly s over s square plus omega 0 square. Now, of course, when we add again z1 and z2, or rather the operation z1 of t minus z2 of t will give us cosine omega 0 t. However, cosine omega 0 t does not have a Laplace transform because the convergence regions ROC1 and ROC2 have empty intersection. And we are not, it's not possible to obtain the, or calculate the Laplace transform of cosine omega 0 t. So either it has to be cosine omega 0 t u of t, or its left-sided version minus cosine omega 0 t u of minus t, so that we will be able to handle the convergence of the integrals. Okay. Maybe at this point you have realized the following. When we have a right-sided signal, we have to deal with only the behavior of the integrand at as t tends to plus infinity. And for the left-sided signal, we have to deal with the case for the integrand as t tends to minus infinity. But when we combine them to form the complete sinusoidal signal, cosine omega 0 t, t between minus infinity and plus infinity, we are not able to handle convergence as t tends to infinity and minus infinity simultaneously. That is the simple explanation behind this analysis. Okay, thanks for watching.